Welcome everyone. Today we're going to be talking about what determines the actual three-dimensional shape of a molecule. The theory behind this is known as the VSEPR model, and it's an acronym which stands for Valence Shell Electron Pair Repulsion Theory. And what this does is that it is responsible for predicting the three-dimensional arrangement of atoms in a molecule. Now, the shape of a molecule is responsible for many physical and chemical properties that molecules have. For example, the shape plays a role in determining whether the molecule is polar or nonpolar. And what causes these shapes to form has to do with the repulsion between the valence electrons. You see, electrons, they don't like each other, so what they're going to do is they're going to try to get as far from each other as possible. And the molecule's shape results from the electrons moving as far apart from each other. You see, as they orient themselves to be as far from each other, they end up predicting the outcome of the three-dimensional shape. If you look here, if you have an example of two atoms connected together, let's call it atom A and atom B, the shape will always be linear. However, if there are more than two atoms forming a molecule, the shape will depend on the number of electrons around the central atom. For example, the element beryllium has two valence electrons. So those dots, what they're going to want to do, they do represent electrons. They want to get as far apart from each other as possible. So what this dot over here is going to do is it's going to orient itself. It's going to actually move over to the side. I'm going to go ahead and show you that. And by placing itself and being on the opposite side of the other electron, it's as far apart from each other as possible. So if it gets together with, let's say, any other element, we'll call it atom X, the other atoms will bond like this on the sides, and you'll form a linear structure. Now, another example, for instance, could be the element, let's say, boron. Boron has three valence electrons. So how will the three orient themselves to be as far apart from each other as possible? Well, think about it. If those three dots that I drew, and I'm going to go ahead and erase this, were to orient themselves like this, notice that they are equidistant from each other. They are also as far apart from each other as possible. And this will predict the outcome of the shape. You see, the atoms that will bond, we'll just call it X again, will bond at these angles, creating sort of like a triangular shape. And we can continue to do this with the rest of the elements. I can use carbon here. Carbon has four valence, and you'll see that the structure that's going to result from this is going to be a tetrahedral structure, and we'll see this now in 3 dimensions. So notice the purpose of those valence electrons around the central atom is that they're going to orient themselves and they're going to try to be as far apart from each other, and that will determine the outcome of the 3-dimensional shape that will result. Now, here's what we're going to do. We're going to look at something called electron geometry. Okay, the electron geometry is based on how many domains are surrounding the central atom. Now, when I say domain, a domain can be one of two things. A domain can actually be an element or an atom connected physically to the central atom, or it could be what we call an unshared electron pair. Okay, so it's an unshared electron pair, which you'll hear me refer to it as lone pairs. Okay, so when you hear me say lone pairs, that's basically an unshared electron pair. It's represented by two dots. The dots represent electrons. So notice there are 3 electron geometries here. The first one is AX2, which simply means that there are 2 atoms joined to the central atom. That's linear. The next one is going to be the AX3, and you'll notice that one has 3 atoms, and as you saw earlier, it's going to form a structure called a trigonal planar. And then the one that has 4, I'll try to draw this as best as I can in 3D. Kind of looks like a little tripod in 3D. Kind of looks something like that. And that one is called tetrahedral. Again, A is the central atom and X is the peripheral atoms. Now, I'm going to show you that there's a difference between what is called electron geometry versus molecular geometry. When I say molecular geometry, it's the actual shape of the molecule, which is determined by the atoms. When it's an electron geometry, that has to do with the atoms connected to the central atom as well as the lone pairs. Follow along with me as I explain this. Here we have the AX2. AX2 is, notice, there are 2 domains, and both domains are physical atoms. So, as you can see, the atoms are arranged on opposite sides of each other. See how the electrons got on opposite ends? Notice it is a linear structure, and the angle, and think of geometry, the angle of a straight line is 180 degrees. Now, the next electron geometry is known as the trigonal planar. It would be, it has 3 domains, and if you notice, there are 3 atoms arranged kind of like a triangle. And if you look carefully, the angle, which is something I want you to also learn and just memorize this, the angle in a trigonal planar is 120. Think about it. You see it here drawn. Here's another 120. Here's another 120. That adds up to 360. You could see a circle that I did there, but each angle is 120. Now, notice the AX4, the 4 stands for tetra or tetrahedral, and this one has 4 domains. Notice in the drawing here, it's much more realistic. It's 3-dimensional. It is not flat. If you think it looks something like this, I'm using methane here as an example. This is inaccurate because this appears to give it a 90-degree angle. And when you're tetrahedral, it is actually not arranged at 90 degrees. Each angle is 109.5 degrees. Now I'm going to show you the difference between what is called electron geometry versus molecular geometry. The electron geometry that you saw here on the first one was linear. Okay? We're going to break these down by category. So I'm going to go ahead and show you here. Here's the first one. The electron geometry is linear. And what we're going to do is we're going to divide this into what is called a bonding pair versus a non-bonding pair. So let's go back over here. And when you have something linear, you have A, you got X, X. And notice that both the 2 things surrounding, the 2 domains surrounding the central atom happen to be atoms. So we're going to call the atoms the bonding pairs. We're going to call a set of dots or lone pairs as a non-bonding pair. So going back over here, in the linear structure I just drew, both were bonding pairs. There are no lone pairs. And the molecular geometry has the same name as the electron geometry. They're both called linear. And if you recall, the angle is 180 degrees. Carbon dioxide is an example of something linear. Now, let's take a look at the domain or the electron geometry that has 3 domains. That electron geometry is called trigonal planar, but what you're going to see is that there are 2 examples. It could be either 3 bonding and 0 non-bonding, which would look like the one drawn here. It'll look something like this. Notice that this has 3 domains, and all 3 of them are atoms, so it has 3 bonding domains. You don't see any lone pairs here, so it's 0 lone pairs. And when you look carefully at this, you'll notice it's trigonal planar. We'll go back over here. notice that when all three are bonding with zero non-bonding, the electron and the molecular geometry share the same name. They're both called trigonal planar. You saw that the angle is 120 degrees. Now, I'm going to show you a scenario where you have still three domains, but two are bonding and one is non-bonding. Okay? Look at this. The structure is going to be AX2E, where E represents an electron pair, an unshared electron pair, or a lone pair. So a general drawing would look something like this. You have this over here. You have X, X, and then you have a lone pair. Notice, this has three domains, but out of the three domains, two of them are atoms. So two of them are what we call bonding, and one is a lone pair, which is non-bonding, and that's how we get this number down here. Two are atoms, one is a non-atom. You could see the example over here with the you'll notice here the nitrite polyatomic ion. Notice that there are two bonding atoms here and one non-bonding there, okay? And then the angle to this is actually not exactly 120. See, the lone pair at the top has a little bit more repulsive force, so it kind of squeezes and makes the angle between the oxygens at the bottom. Let me go ahead and point this out. So the angle down here is actually a little less than 120 degrees. Okay? So, and that's due to the lone pair having a little stronger push, so it closes the angle and it makes it just slightly under 120 degrees. Another classic example, we'll see a couple more of these, is ozone. Ozone is a structure that also has a bent structure. Now notice, and I forgot to mention this, notice that the electron geometry is still trigonal planar. The electron geometry has to do with the total number of domains. If you have three domains, you're trigonal planar. However, out of the three domains, two of them are bonding and one of them is non-bonding, and that has to do with the lone pair. So the molecular geometry, which is the actual shape, will not be called trigonal planar. It has a new name and it's called bent. Okay? Now, here's what we're going to do. We're going to look at the, let's go back for a minute, and we're going to look now at the domains. So we've done two domains, three domains. Let's go over here. And now we're going to look at something that has four domains. And when all four domains are bonding, so we'll do one of these. I'll do my best here. Let me go ahead and put the central atom here. And I'll try to make this tetrahedral as best as possible. So here, when all four domains are bonding and there are no lone pairs, the electron geometry for four domains is called tetrahedral. And if all four are bonding, the molecular geometry is also called tetrahedral. You could see here methane, CH4. The angle is 109.5 degrees. Now, what I'm going to show you is what happens if three are bonding and one is non-bonding, or if it's two and two. Now, let's go back and let's take a look at this. So, if you have a scenario where you have a central atom and you have, let's say here, three are bonding and you have a lone pair. Notice you still have four domains. So you still have a tetrahedral electron geometry. However, three of the four domains are bonding, and the one of the domains is a non-bonding, which is that lone pair that you see at the top. So when we go over here and check our example, we have ammonia here. Notice that ammonia has the lone pair up here, and then you have the three domains here with the hydrogens. So you have a 3-1 breakdown. So the name will not be called tetrahedral. this one has a new name. The molecular geometry is going to be called trigonal pyramid. Sometimes you might see the word pyramidal. So trigonal pyramid or pyramidal can be used to represent this one. Now, again, because the lone pair pushes a little bit more, has a little extra repulsive force, you're going to see that the angle is actually going to be slightly smaller than 109.5. In fact, the measured angle in ammonia is actually 107 degrees for this particular molecule. But it will be less than 109.5. Now we're going to take a look at one more scenario where you have a 2-2 breakdown. Again, you have 2 bonding and 2 non-bonding. It would look something like this. You have your atom in the middle. You have your 2 bonding. And then you have 2 electron pairs or lone pairs. Again, you have 4 domains here. But out of the 4, you'll notice that 2 are bonding domains. And 2 are lone pairs, which are your non-bonding domains. Okay? And again, remember that tetrahedral normally has a 109.5 degree, but these guys also kind of like repel each other. Not only are they repelling over here, they're also repelling each other. They want to get as far apart from each other as possible. So if you look over here, you'll see how everything is equidistant. Now, one of the most popular structures that has this shape, which, by the way, even though it's a tetrahedral electron geometry, you'll notice that the name of this shape is bent, okay? Just like the one we saw previously, this one is also called bent. Water is probably the most popular example. Water, when you draw it, looks something like this, with the hydrogens out here, okay? Let me draw that a little better. And what happens is the angle, we already know it's going to be less than 109.5, but the angle's even smaller than the previous example because there's 2 lone pairs. The angle in water has actually been measured to be about 105 degrees. You might see some textbooks say 104.5, but 105 degrees is the angle between the hydrogens in a water molecule. And again, that's less than 109.5. So notice that there are 2 bent structures. Okay, we have a bent with 1 lone pair that we saw earlier, and we have a bent with 2 lone pairs. Okay, the one we just saw falls under the tetrahedral electron geometry because there are 2 bonding and 2 non-bonding. There are 4 domains. So this is a breakdown of these shapes. Now, what we'll do is we'll put this into practice. We have a couple of examples here. First, we'll start with NF3. And if you remember, N has 5 valence. Fluorine has 7. Let's multiply. There's only 1 nitrogen there, but there's 3 fluorines, which is 21 plus 5. That'll give us 26. So we're going to put nitrogen in the middle, and we're going to put the fluorines. Remember that fluorine can never go in the middle. And then we connect everybody to the central atom. We're going to give everybody an octet. Always start with the peripheral atoms. Okay, so we're going to give each fluorine 6 dots. Now they have an octet. Now nitrogen needs 2 dots. Now everybody has an octet. Now our magic number, which is our total valence, is 26. When we count what I drew up here, you'll notice there are 26 electrons. You can see here 1, 2, 3, 4, 5, 6, 7, 8 is the line. 9, 10, 11, 12, 13, 14, 15, 16 is the line. 17, 18, 19, 20 is the line. 21, 22, 23, 24, 25, 26. We have a perfect match. That means that this is the correct Lewis dot structure for NF3. Now, if I asked you for the electron geometry, this guy has 4 domains. It has 3 bonding and one non-bonding. You can see the lone pair appear. So the electron geometry would be tetrahedral. Now, when they ask you for the molecular shape, as it does in this question, they're actually referring to the molecular geometry. So the molecular geometry is not going to be tetrahedral because in this particular example, there's a breakdown. Out of the 4 domains, 3 are bonding and 1 is non-bonding. And the name of this shape, we can go by 2 names. We can either use trigonal pyramid, and some books call it pyramidal. So either of these 2 names would apply to describe the molecular shape. And then as far as the bond angle, this angle is going to be less than 109.5. A lot of times it's about 107, but less than 109.5 would be sufficient. Okay, so that would be our first example. Let's try one more. Here we have a polyatomic NH2 negative. Okay, this is just a semicolon at the end there. That's not an electron pair. So we're looking here at NH2 negative. So again, we got nitrogen with 5 valence. Hydrogen has 1. We got 1 nitrogen. We have 2 hydrogens. Add that up. But remember that the negative means we're going to add 1 extra electron, and our magic number, our total valence, is 8. We're going to put nitrogen in the middle, and we're going to put the 2 H's in the periphery, and then we're going to connect them like this. The next thing we're going to do is give everybody a valence. Now remember that hydrogen does not need 8. He's already happy. So the only guy that really needs valence electrons is nitrogen needs 4 dots so that it is now has the octet. Okay. Now remember, this is a polyatomic, so we need to put a bracket. We need to put the charge in the corner. And look what I'm going to do. I'm going to redraw this. Since if you look carefully, and you'll see why I'm redrawing it, okay? You could leave it like that, the way it's drawn, but I'm going to draw it like this so it can be a little bit more three-dimensional, a little bit more visual. Notice the electron geometry has to do with the total number of domains. This molecule has 4 domains. It has 2 hydrogens, which are 2 bonding, and it has 2 lone pairs, which is 2 non-bonding. So the electron geometry is also tetrahedral. Now, the shape has to do with the molecular shape. If you look under tetrahedral, when you have 2 bonding and 2 non-bonding, the name of this shape is called bent. And the angle is going to be less than 109.5 degrees, probably closer, like water, to 105. But again, less than 109.5 would be sufficient. So notice that it is important that you are able to distinguish between the electron geometry versus the molecular geometry. The electron geometry has to do with the total number of domains, which includes the atoms, which are bonding, and the lone pairs, which are non-bonding. The molecular shape has to do with the breakdown of bonding to non-bonding. Like in this example, 2 bonding and 2 non-bonding would put it as a bent as far as the molecular shape. So hopefully this gives you a good understanding to some of the basic shapes covered in VSEPR theory.